Okay, the first two applications that we're going to see for integrals are going to be accumulation problems and then average value problems. Okay, so in an accumulation problem, you are being given a rate. So we'll have that rate as r of t at which something is happening over an interval. So we'll say that that interval is from A to B. It's usually a distance in time. Okay, so if I have, one way of visualizing this is like it's a leaky tank problem. Water is leaking out of the tank over at a given rate with respect to time over a given interval of time. So the question is like, well, how much water has leaked out of the tank all total over that interval of time? And the answer to that is that's equal to the integral from A to B of the rate at which it's occurring, and that will give me the accumulation of whatever is being dispersed over time at that rate from time A to time B. So let's give this a very practical application. All right, so let's say that water is leaking out of a tank at a rate of the square root of t plus 1, okay? And it's doing this for 3 minutes, okay? And the question is how much, so this is the square root of t plus 1, let's say it's leaking out at like cubic centimeters, and how much has leaked out over 3 minutes. Now this is pretty real because this thing is going to continue to leak out, but at the end of the day, the rate at which it's coming out is changing over time. So the volume of the water that would leak out in 3 minutes would be the integral from 0 to 3 of this t plus 1 to the 1/2 dt. Now, I don't have to deal with the chain rule because the derivative of the inside here is 1. So this is 2/3 t plus 1. In the problem in the notes, this is gallons, not cubic centimeters, so we're going to make it gallons. 2/3 t plus 1 to the 3/2, right? From 0 to 3. If I put 3 in there, I get 4 to the 3/2. And if I put 0 in there, I get 1 to the 3/2. And the definite integral here is going to be 2/3. Let's see, the square root of 4 is 2 times 3 is 8 minus 1. So this is 7. So that's 14/3 of a gallon have leaked out in 3 minutes. Okay, so what is that? That's like 4 2/3, right? 4 2/3 gallons would have leaked out in that time. So this is like the classic example of an accumulation problem. Let's take a look at a second example where it's not water, but it's something else that's accumulating. Okay, so we have a company, it's selling cable, and it is making a revenue of $120 per meter, okay, of cable. Now, to produce that cable, if you produce, so there's a sense of like the rate of the cost here. So my cost function is going to be 6 times the square root of x, right? Dollars will be the cost, total cost, when I produce per meter, when I produce X meters of cable. Okay, so this is the rate of my cost. This is the rate of my revenue, and this is all per meter, right? So what am I going to do? Well, what I want to do is I want to maximize my profit, right? Or I want to know what my profit is. So what is my profit when I'm selling, let's say, 25 meters of cable, right? So this is going to be the integral from 0 to 25, right, of my revenue, 120 per meter, minus 6 radical x per meter sold at that given meter, right? So we work the integral, I get 120x, right? So this is again going to be x to the 3 halves. So 6 times 2 is 12 thirds from 0 to 25. So that's 120x minus 4x to the 3 halves from 0 to 25, right? So this is going to be, let's see, 120 times 25 minus 4 times, let's see, 25 to the 3 halves. Then it's going to be minus 0, right? Because at the 0 time, I'm not having any revenue or any cost. So let's see, if I work that out, 120 times 25 minus 4 times, let's see, 25 to the 3 halves is going to be 125. I think that comes out to be $2,500. Okay, so my revenue in this is ultimately coming out as $2,500 for selling 25 meters of cable at $120, where it's costing me 6 radical x for each meter that I'm producing. So, all right, there we go. So this is the idea of an accumulation problem. Okay, so let's say the other example here we have are what are called an average value problems. Okay, so now I have a function and I want to know the average value of that function over a given interval. So the average value of some function f over some given interval a, b. Well, it kind of follows from what we did before, because like I want to add up all the values of f, right? So that would be take the integral from a to b of f of t dt. Well, I think in the notes I made it f of x dx, but it doesn't much matter. F of x dx, right? But then I had to divide it by the width of the interval. So that's 1 over b minus a, right? Take the sum and divide it by the number of values. Okay, so let's do a quick example here. I'm going to actually start a new slide for that. Okay, so what I want to do here is find, so let's say f of x is 1 plus x squared, and I want the average value for f of x on the interval from -1 to 2, right? So this is going to be 1 over 2 minus -1 times the integral from -1 to 2 of 1 plus x squared dx. So this is 1/3, and then what's that? Let's see, this is going to be x plus 1/3 x cubed from -1 to 2, right? So this gives me 1/3 times, so if we put the 2 in there, we get 2 plus 8/3 minus, let's see, -1 minus 1/3, right? So let's see, that's 1/3. 2 plus 1 is 3. 8/3 plus 1/3 is 9/3. So let's see, that's 3. 9/3 is another 3. So this is 1/3 of 6, which means the average value is 2. All right, so that's like a real simple example of using the average value. Let's look at one more that involves like a trig function here. Okay, this time we're going to say f of x is equal to the sine of 4x, and we're going to be an interval from -pi to pi, right? So the average value here should be 1 over pi minus negative pi times the integral from negative pi to pi of sine of 4x dx, right? So this is 1 over 2 pi, right? 1 over 2 pi. So let's see what happens next here. I have sine of 4x dx, so the antiderivative of that is going to be negative 1/4 cosine of 4x from negative pi to pi. So let's see, this is negative 1 over 8 pi times cosine of 4 pi minus cosine of negative. So it's going to be negative 4 pi, right? So let's see, that's negative 1 over 8 pi. The cosine of 4 pi is 1. The cosine of negative 4 pi should also be 1. So this goes to 0, which means this whole thing just goes to 0. So if you kind of think about what's going on with this curve, it means that on average, this curve is below the 0 just as often as it is above the 0. So there we go. Accumulation problems and average value problems.